In this video, I'd like to share more information with you about Unit 2, Part 1, Lesson 2, and we'll be discussing the increasing and decreasing portions of functions, or when they remain constant. If I'm ever referencing notes and you see this symbol here, this little triangle with a squiggly line through it, that's what our textbook likes to show when we're discussing something in pre-calculus class that's directly related to a portion of calculus. And this definitely is a portion that shows up a lot in our calculus class. In fact, the study of calculus really, the majority of Calculus 1 is determining how steep curved lines are. Can we apply a steepness, or in a sense a slope, to curved lines? And if you recall, slope with regards to linear functions, a slope indicates when a function is increasing or decreasing. And so visually, I think we can establish when these functions are increasing and when they are decreasing. And so in this particular case, I would say that the function is decreasing along this section of the graph. And then if we keep marching along following this blue function, we see that it decreases again over here. Remember, when we say increasing or decreasing, we're talking about as we move from left to right. Now the function appears to be increasing from here, where it switches from decreasing to increasing. And again, as we're marching from left to right, we're increasing, we're increasing. We hit a point where we level off, so we're not increasing anymore. We're definitely not decreasing, though, either. So at that point where we level off, we would say we remain constant. Now at these points of transition, imagine that you're able to, zoom in infinitely close here. If you're able to take a look at that graph as infinitely close as you possibly could, it would be difficult to determine, or impossible to determine, right at that specific spot whether the graph is increasing or decreasing. Same thing here. At this particular spot, we can't really say that the function is increasing or decreasing. It's at a point of transition. Now here, even though that's a point on the graph, we would say that the function is continuing to increase all the way through that point. We haven't reached a point in which we level off. So that one's not going to be a point of transition, but these other 3 points are. Additionally, at these endpoints, we don't really know what's happening to the left of this graph or to the right. And if the function itself stops right there, well, it's decreasing up to this point, but at that specific spot altogether, it's hard to tell whether that's increasing or decreasing beyond it. So we don't want to include the endpoints with our notation for increasing or decreasing either. So let's use interval notation and see if we can identify the x values for which the function is increasing. Well, again, we said the function was increasing from here to here along this blue pathway. Our x values exist from -4 up to 0 along the x-axis. And we're not going to include these endpoints because it's hard for us to tell, and it's virtually impossible for us to tell with the graph whether the function is increasing or decreasing at those specific points. If I were to note this with set notation, we would say something like this, that from -4, which is less than x, which is less than 0, the function is increasing. To build out the set notation completely, we would use additional phrasing like this, and we would say out loud the set of x's such that -4 is less than x, which is less than 0, represents our interval of increasing behavior. For our decreasing portion, well, we've got 2 sections here. The function is decreasing on x values that are an element of the group from -6 to -4, as well as the group from +3 to +6 on the x-axis. So we would use a union symbol since the graph is decreasing on this interval and this interval. With set notation, we might say something like this: the set of all x's such that negative 6 is less than x, which is less than 4, negative 4, and 3 less than x less than 6. Sorry about the noises in the background. I'm not sure if you can hear that on the microphone, but they're drilling holes across the way in a different classroom. Now, as far as our portion of the function being or remaining constant, we would say that it is constant amongst the x values that are in between 0 and 3. And with set notation, we would say that the set of all x's such that 0 is less than x, which is less than 3. And there we have it. If we have to report when a function is increasing or decreasing, and we're doing so using algebraic notation, we've identified with either interval or set notation when the function is increasing, decreasing, or constant. So let's try these three graphs on your own here. Can you tell me when the function is increasing, when it's decreasing, and when it remains constant? Pause the video now and resume playback in a moment to check your work. So I've used interval notation to identify where the function is increasing or decreasing, or where it remains constant. In part A, I made the claim that it's increasing from 0 to 3, and again from 4 to 5 along the x-axis. And I'm claiming that it's decreasing from 3 to 4. And notice that I did not include 3 or 4 as an endpoint in either of these cases, because that's a point of transition. It is neither increasing nor decreasing at those specific spots. For part B, again, we're increasing from this position on, and we're decreasing from here to here. So increasing from 3 to 5 along the x-axis, decreasing from 1 to 3. This open circle tells us that there is no coordinate there whatsoever. So the graph appears to be decreasing from left to right towards this position, and increasing from left to right from that position, but there is no actual coordinate at that particular spot at the bottom of that curve. We'll discuss more on that a little bit later. And in our final example here, we're increasing from an x value of 2 to 5, decreasing from an x value of 0 to 1, and then we remain constant from x values 1 to 2. Again, did not include the transition points or the endpoints of this graph for our notion of increasing, decreasing, or remaining constant. And I think these answers or these solutions would be satisfactory on any test or quiz. In calculus, one of the major reasons why we discuss increasing versus decreasing portions of a function is so that we can determine where a maximum or a minimum point on a graph is. And these are plural forms of the word maximum and minimum, because there could be multiple maximum points and minimum points along a stretch of a graph, and each one would be considered a local max or a local min. For every function on a given domain, there is going to be a global or absolute maximum, or a global or absolute minimum, and there's generally just one of those, although it is possible to have more than one. It would be the most maximum point or the least minimum point, and these are often called extreme or extremes. And in our calculus class, we like to discern between local maxima and global maxima within a domain of a function. So in this particular example, we're being asked here, at what values of x does the function have a local maximum? So where is there a high spot on this graph? And right here is a local maximum. We wouldn't say that these tails are local maxima points, because again, these tails imply that we're increasing upward forever and ever in that direction. And since they're continuing to increase upward, we can't say that they're at a high spot in the graph. They're not at a local maximum point. But the local maximum does occur right here. We could say that there is a local maximum at x equals 1, and that maximum point is the coordinate 1, 2. Same question in part B. What values of x, if any, does f have a local minimum? Well, here's a local minimum, and here is a local minimum. We have two local minima. So those occur at x equals -1 and again at 3. And the points are -1, 1 and 3, 0. Those are the two spots on this particular function where local minima occur. So if we start answering part C, we should see something kind of interesting occur. Find the intervals where the function is increasing and find the intervals where the function is decreasing. Well, the function is decreasing from left to right along this edge and this edge, or that section of the graph, and the function is increasing from here to here and here to here. So we could say that the function is decreasing on all x values that are an element of the group from -infinity to -1. So from -infinity to -1, -infinity to -1, and then again from 1 to 2. Whoops, sorry, that should be 1 to 3 on the x-axis. And then we could say that the function is increasing from -1 to 1 on the x-axis, along with 3 to infinity on the x-axis. And what I wanted to point out here, and this is part of what we call a derivative test in calculus, is that when we transition from a decreasing function to an increasing function, the graph exhibited a minimum. Again, if we change from decreasing to increasing, that created a minimum point. And we see that over here too. The graph was decreasing and it switched to increasing, so we found ourselves a minimum. If, as we move from left to right, we go from an increasing function to a decreasing function, then we find ourselves at a maximum point. So here again, we have an increasing function that switches to a decreasing function. We found ourselves at a maximum. Now, this is only true when the point of turnover, the point at which they change, is defined. This is kind of an interesting concept, but back here we were switching from a decreasing function to an increasing function, so we might think that there's a minimum at this spot, but in actuality, since the point is undefined at that location, there is no minimum here. There's no lowest spot on this graph, because again, if we could zoom in infinitely close to this particular point, this graph from the right is always getting a little bit lower. This graph from the left is always getting just a little bit lower. There is no lowest point defined in this particular shape. So even though we are transitioning from a decreasing to an increasing function, the point at the transition is not defined, so we would say that there is no minimum here. So using algebraic methods, or if you'd like to memorize this algebraic definition in this box, you could then describe or identify maximum and minimum points within a function, even if you don't have the graph available to you. And again, that's a pretty important understanding, or a pretty important component of our calculus class when you get into there next year. Well, I hope this video helps you out with the notion of maximum and minimum points, along with increasing and decreasing values. If you have further questions, please let me know, and I'll do my best to answer them. Thanks for watching.